In this video, we're going to talk about a differentiation method called implicit differentiation. It is actually an option that you have. It's a nice option many times, but it's just another way of finding the slope of the tangent line, aka the derivative. So before we do that, I just want to maybe talk a little bit about how to differentiate with respect to different variables. So you might be used to this notation where at this point you might just say, all right, I know what this means. It means find the derivative of this. So you know what to do. You go here and say, all right, power rule. So I'm going to say 3x squared plus 6x minus 9 plus 0. So we're done right there, and that's your answer. And you knew that meant find the derivative of this. Okay? So look at this next one. It says differentiate with respect to x. So let's look behind the scenes. What's really going on in this notation and why we write this the way we do. This d right here is a small change. So you might want to compare it to the sciences where you have like delta T for the change in temperature. So this d could mean a change in, or it does mean a change in. It could mean delta, or another way to think about it is a small distance. Okay, so what this is actually asking you to do is to compare small differences in these things and compare it to small differences in x. Small differences in all these things, compare it to small differences in x. So when we hear differentiate with respect to x, we're going to work with this equation and do that. So we can do anything we want to an equation as long as we do the same thing to both sides. So I am going to differentiate both sides of this equation with respect to x. So that's how this looks. So look at small differences in y and compare it to small differences in x. Okay, so that's the derivative. So if we do that, we get 1, derivative of y is 1, but we just are looking at small differences in y and comparing them to small differences in x. Here, derivative of this, small differences in this, the derivative is 3x squared, and we just looked at small differences in x and are comparing them to small differences in x. So now look what happens here. We know dx, something divided by itself, is 1, and that's no different here. dx divided by dx is 1. Next one, 3x squared, derivative of that is 6x, and we just, again, small differences in x compared to small differences in x. I'm going to write them out on this one, but from here on out, I will, if I have a dx, I'm not going to write it. I think it in my head, but I'm not going to write it. Minus 9 dx, which is 1, plus 0 at the end here. So when I simplify, we get dy dx equals 3x squared plus 6x minus 9. Notice it's the same thing up here, but hopefully we have a little more insight about what's going on. Okay, so this next problem says differentiate with respect to t this time. Throughout your Calc 1 here, I would say 95% of the time you're either going to be differentiating with respect to x because it has to do with slope, or you're going to be differentiating with respect to WRT, with respect to t, because that has to do with time. You'll be doing something later called related rates. And I have a video on that too if you need help with that. So I'm going to differentiate both sides with respect to t. And so when I take the derivative of y, I get 1. I'm not going to write the 1 here, but small differences in y compared to small differences in t. Here we get 3x squared. This time we get dx dt, right? Because we just compared little differences in x, and we're comparing them to little differences in t. So this, notice, doesn't cancel to 1. Next one is 6x dx dt minus 9 dx dt, and then we have the plus 0 there. So we're done differentiating that with respect to t, and that's how we're going to leave our answer there. Again, you'll have a use for this pretty soon in your class. All right, now we need to talk about explicit versus implicit. Explicit means it's very apparent what it is. It's in your face. So this equation right here, y is explicitly solved for in this equation. You know exactly what y is. Y is this. That's the definition of explicit. Implicit means it's a little more secretive. It's more so implied. Okay, it's hidden a little bit. And notice that y is not isolated. It's not by itself. This is an equation where y is implicit. And if you look at them, and actually I'll just show it to you here, these two are the exact same function, just written a little, and one is implicit, one is explicit. Let me just show you here. So if I take that radical x plus radical y equals 4, and I solve it for y, so subtract radical x, and then I square both sides to isolate y, there you have the explicit form of this, and you saw that right here. Okay, so you many times will have an option. So take a look here. I'm going to differentiate both of these with respect to x so that we have our slope, our derivative. So that would look like differentiate this side with respect to x and differentiate this other side with respect to x. And we could write y prime. I'm going to keep this notation dy dx. And we're going to use the chain rule here. So that's 2 times the quantity 4 minus radical x raised to the first power times the derivative of what was inside of there. So that's negative 1 over 2 radical x. And we can simplify that a little bit. So dy dx equals, the 2's are going to cancel. We have this negative 1 on the top. And we have this 4 minus radical x on the top. And we have a radical x in the denominator. I'm going to stop there on this one. You could maybe say rationalize the denominator, but you don't have to. All right, let's look at this one over here. We're going to differentiate this, both sides of this equation, with respect to x. All right, so when we do that, derivative of this is 1 over 2 radical x, dx dx, again I thought it, I didn't write it, plus 1 over 2 radical y, this time it's dy dx, we differentiated y with respect to x, and that's equal to the derivative of 4, which is 0. All right, let's solve this for dy dx. I think I'm going to start by multiplying both sides by 2, just to make it easier to work with algebraically. I'm going to subtract that term. Now I'm going to since that's in the denominator, I'm going to multiply both sides by radical y. So here's what we're looking at. Multiply this side by radical y. And there's our answer here. So you think about it, and it looks kind of weird at first. These are the same equation, different forms. So these are both correct versions of the derivative. Notice this one's all in terms of x. This one is in terms of, this derivative is in terms of y and x. Just to show you that they're the same, if you look at this, and we think about what radical y is equal to, isn't radical y equal to 4 minus radical x? So if we substitute that right here, and we substitute that with 4 minus radical x, do you see that that's right here? It's the same thing. So negative that over radical x, and it's here too. Okay? So you might be asking, well, this process seems a lot more difficult than this process over here, so I'm just going to stick with explicit. There are some benefits to implicit differentiation, and I just want to show you one here. So take a look at this equation. Notice where y is. It's definitely implicit, and it would be a pain to get y by itself. You'd have to use, let's see, an inverse sine function, and then you'd have to use a square root function, and more involved in that. But so in this form, implicit differentiation is going to be your best bet. So let me show you how that works. We're going to differentiate both sides with respect to x. Okay, so when we do that, Derivative of 1 is 0. I'm not going to write that. Derivative of x is 1 dx dx. I'm not writing the dx dx, so we just have 1. Over here, we have a composite function. This function is inside of a sine function, so we're going to have to use the chain rule. And also, here's a product. So, chain rule, product rule first. Look, I'm just taking the derivative of a quantity with y with respect to x. So here's that notation. First times the derivative of the second plus the second quantity times the derivative of the first. So that one, I'm taking the derivative of x, which is 1. And again, I'm just thinking it dx dx. It's right there. I don't have to write it. All right, a little bit of simplifying here. We have 1 equals the cosine of xy squared times 2xy dy dx plus y squared. And our goal is to find the derivative, so we're going to solve for dy dx. A couple ways to do this. I think the easiest way is going to be to divide by this quantity here. So if we divide by that quantity on both sides, we have and the next thing we're going to do is subtract this term. So we have and the last thing we have to do is divide by 2xy. So over here we'll have what we wanted, our first derivative. And over here when we divide by 2xy, we're going to get cosine of y xy squared minus, and then dividing this by 2xy. And we could reduce the y's there. I'm not going to waste time on this video to do that. So here's your answer. Just make sure you show that reduced.